The cosmos is a vast, enigmatic expanse full with oddities that make it difficult for humans to understand space-time and the idea of reality itself. Black holes are among the most mysterious of these phenomena. They are enormous Goliaths that devour everything in their path, even light. These objects in space, formed from the remains of massive stars, with gravitational pull so great that it bends the very fabric of reality. Modern technology, especially the James Webb Space Telescope, JWST, has allowed scientists to study these unusual objects in more detail and is changing our view of the cosmos. Not just any old celestial object, black holes are areas of space where gravity is so strong that nothing can escape it, not even light. This makes it very difficult to immediately detect them. Supermassive black holes, which are the largest of them, are found at the centers of galaxies and can have masses that are millions or billions of times larger than the Sun. Astronomers study and debate their creation and growth in great detail. It is thought that the relics of dying stars gave rise to these supermassive black holes, but the precise process by which they developed is still one of astronomy's greatest mysteries. When a giant star runs out of atomic fuel, it collapses catastrophically due to its own gravity, and if the star is large enough in mass, it can produce a black hole. By absorbing matter from its surroundings, the ensuing black hole grows larger and larger. Frequently, this results in the formation of a whirling gas and dust accretion disk that spirals into the black hole, heating up and radiating intensely. A significant milestone in the study of cosmology was reached in 2019 when the Event Horizon Telescope took the first picture of a black hole. The world was able to visually verify the existence of black holes thanks to this image, particularly the supermassive black hole in the center of the galaxy M87, which is situated about 55 million light-years away from Earth. This amazing image displayed the event horizon, or the point beyond which nothing can escape the black hole's gravitational attraction, as a dazzling ring of light encircling a dark shadow. In addition to being a work of art, this historic photograph validated numerous predictions made by Einstein's general relativity theory. In order to obtain this image, a global network of radio telescopes had to be coordinated, essentially forming an Earth-sized virtual telescope. This accomplishment has established that black holes are actual things that are essential to the development of galaxies and has created new research opportunities for these enormous monsters. Although the discovery of the black hole in M87 was a significant advance, efforts to verify the existence of black holes date back considerably longer. Cygnus X1, the first credible candidate for a black hole, was found in 1964. Compared to supermassive black holes, Cygnus X1 is a stellar mass black hole. However, its findings signaled a paradigm shift in our understanding of these mysterious things. Situated in the constellation Cygnus, approximately 7,200 light-years away from Earth, it is a component of a binary system that is partnered with a large blue supergiant star. The X-rays released when material from the companion star is pulled into the black hole's accretion disk are used to infer the black hole's existence. The first conclusive proof that black holes were actual, observable events rather than merely speculative things came from the detection of these X-rays by early space-based observatories. Prominent physicists including Stephen Hawking and Kip Thorne expressed both enthusiasm and doubt about the discovery of Cygnus X1. They famously wagered on whether Cygnus X1 was, in fact, a black hole in 1975. Hawking, who was more circumspect, disagreed with Thorne's assertion that it was a black hole, given his confidence in the data. Hawking gave up the bet in 1990 when the evidence for Cygnus X1 being a black hole grew stronger with more observations. An important advancement in the study of black holes was made when Cygnus X1's status as a black hole was established. Black hole detection and research remain extremely difficult tasks, despite theoretical predictions and indirect evidence. Since black holes don't release light like stars do, they are unseen in the vastness of space. To find black holes, researchers use their influence on neighboring objects. This entails tracking the movements of stars and gas clouds around these occult objects and looking for X-rays released by material being drawn into the black hole and cooked to extremely high temperatures. The requirement for sensitive and accurate sensors is one of the primary obstacles in black hole detection. Black hole accretion disks release X-rays and other radiation. although these are frequently weak and quickly overwhelmed by other cosmic noise sources. Furthermore, because many black holes are very far away from us, the signals they send back to us are quite weak, necessitating the use of sophisticated tools and methods in order to discover and interpret them. Black hole detection and research have greatly improved with the development of space-based telescopes like the Chandra X-ray Observatory and, more recently, the James Webb Space Telescope. Because they are not affected by Earth's atmosphere, these observatories are able to view the universe at light wavelengths that are otherwise obscured by it, such infrared and X-rays. This has made it possible for astronomers to examine black holes in greater detail and has produced a number of novel findings. The JWST, which will launch in 2021, heralds a new chapter in space travel and black hole study. JWST is intended to explore the far reaches of the cosmos by detecting light that has traveled billions of years to reach us thanks to its potent infrared capabilities. This makes it the best instrument for researching the origins of the universe, the birth of the first galaxies, and the genesis of black holes. JWST's capability to observe in the infrared is one of its main advantages. Because infrared light can pass through dust clouds, which frequently block off visible light, JWST is able to see features and structures that would otherwise remain concealed. Studying the areas surrounding black holes, which are frequently encircled by dense clouds of gas and dust, is particularly crucial. JWST has only been in service for a short while, but it has made several groundbreaking discoveries. One of these is the discovery of a sizable, inactive black hole in the Milky Way galaxy that is close to our solar system. With a mass almost 4 times that of the Sun, this black hole, known as Gaia BH3, is the second closest black hole to Earth that is currently known to exist. Gaia BH3 was not discovered until crucial evidence from JWST and other observatories allowed for its existence to be confirmed. Despite its close proximity, Gaia BH3 is located 1,926 light-years from Earth in the constellation Ophiuchus. It was unintentionally found as scientists were deciphering information from the European Space Agency's Gaia mission, which is charting the locations and motions of Milky Way stars. The finding of Gaia BH3 underscores the power of contemporary telescopes and the mysteries that lie ahead in our cosmic backyard. As a dormant black hole, Gaia BH3 does not release a considerable quantity of radiation because it is not actively acquiring material from a companion star. Because dormant black holes don't emit the brilliant X-rays that are usually associated with active black holes, it is especially difficult to discover them. Rather, the gravitational pull they exert on neighboring stars and other objects suggests their existence. Because it gives astronomers a unique chance to investigate an inactive black hole, the finding of Gaia BH3 is remarkable. Researchers can learn more about this black hole's mass, spin, and other characteristics by tracking the movement of the stars around it. Thus, we are better able to comprehend the life cycles of black holes and the variables that affect their state of activity or dormancy. Although they are difficult to locate, dormant black holes like Gaia BH3 are thought to be somewhat prevalent in the universe. The finding of Gaia BH3 at such near proximity to Earth raises the possibility that our galaxy contains additional dormant black holes just waiting to be found. The JWST mission's capacity to investigate the origins of black holes and the early universe is among its most fascinating features. Within a few 100 million years of the Big Bang, the early cosmos experienced a flurry of activity as the first stars and galaxies formed from gas and dust clouds. It is thought that the first black holes developed during this period, while the specifics of this process are yet unknown. JWST's most recent observations have offered fascinating windows into this far-off past. The discovery of an extremely red supermassive black hole in the early universe, roughly 12.9 billion light-years from Earth, is one of the most important findings. This black hole is one of the oldest and largest black holes discovered to far, with an estimated mass of about 40 million times that of the Sun. The prevailing concepts of black hole generation and expansion are put to the test by the discovery of this red supermassive black hole. Less than a billion years after the Big Bang, a large black hole like this one exists, indicating that black holes can grow far more quickly than previously believed. This poses significant queries regarding the mechanisms underlying black holes' explosive expansion and their interactions with host galaxies. An important question in astronomy is raised by the finding of supermassive black holes in the early universe. Did galaxies or black holes form first? In cosmic evolution, this is frequently referred to as the chicken or egg dilemma. Black hole research not only advances our knowledge of these massive events, but also serves as a catalyst for the creation of novel tools and methods. Astronomers are always creating more sophisticated tools and cutting-edge techniques as they strive to view more and more. These developments enable us to investigate the harsh surroundings of black holes and acquire more precise data regarding their characteristics. The study of gravitational waves, ripples in space-time brought on by huge objects like black hole mergers, is one fascinating field of study. Virgo and LIGO detectors have already seen several dark hole mergers, offering vital details regarding the dimensions, occurrences, and characteristics of these cosmic occurrences. Gravitational waves provide a new avenue for investigating black holes and testing gravity theories. Future missions and telescopes will significantly deepen our understanding of black holes as observational technology advances. Future initiatives, such as sophisticated space observatories, should offer even more in-depth understanding of how black holes behave and interact with their environment. These developments will probably reveal new details about black hole physics, such as their function in the formation of galaxies, the makeup of their interiors, and their eventual demise. In summary, the study of black holes is an exciting and quickly developing field that never fails to enthrall scientists and the general public. With every new finding, we learn more about these mysterious giants and stretch the boundaries of our understanding. We can anticipate learning even more about the actual nature of black holes and their effects on the cosmos as science and technology develop. Scientists are looking into the theoretical ramifications of these findings as we explore black holes more thoroughly. Our comprehension of basic physics is challenged by the mysteries surrounding black holes, particularly the unification of general relativity and quantum mechanics. The information paradox, which asks whether data about matter that enters a black hole is permanently lost or recoverable, is one important topic of study. This discussion focuses on the fundamentals of reality and how data is either destroyed or retained in harsh environments. Furthermore, understanding black holes provides important new light on dark matter and dark energy. Through studying the effects of black holes on their surrounds, scientists are able to deduce the existence of these enigmatic elements of the cosmos. This has the potential to shed light on some of the most important cosmological concerns regarding the composition and destiny of the cosmos. Furthermore, study on black holes may reveal previously undiscovered events or even new varieties of black holes as our capacity for observation increases. For instance, although they are still difficult to find, intermediate mass black holes, which range in size from stellar mass to supermassive, may provide new information about the creation and development of black holes. Similarly, information on the conditions of the early cosmos and the birth of the first galaxies may be revealed by the possible discovery of primordial black holes, which emerged in the early universe. In summary, research on black holes pushes the frontiers of our understanding of the universe as a whole while simultaneously extending our grasp of these cosmic giants. Black hole research continues to be one of the most exciting and influential areas of contemporary science, since each new finding raises more problems and encourages researchers to look for solutions.